All right. Good afternoon, everyone, and welcome back from the lunch break. It's my immense pleasure to announce a good friend and long-term collaborator, Hossein Yalame. Um, Hossein is probably best known for his work on MPC frameworks such as ABY2 and his continuous efforts to bring ideas from hardware synthesis over to MPC optimization. Unfortunately, Hossein couldn't travel here, so instead we'll have his invited talk online. And now to the official bio. So Hossein earned his PhD at TU Darmstadt in 2024, and his work has been awarded the GDD Science Award for Young Academics. Now, since 2023, Hossein is MPC researcher or research engineer at Bosch in Germany, where he is developing and integrating MPC technologies to advance real-world use cases. With that, I would like to hand over to Hossein. I hope you can hear us, and we're looking forward to your talk.
So, perfect. Thank you, Christian. I hope you hear me, just to be sure. You hear me? I hope you hear me.
Yes.
Okay, perfect. So I would say good morning in Germany and good afternoon in India. And I'm happy to be here at TPMPC, but also sad because I couldn't make it. So for that reason, it could be in person, but now it's online. So that's life. We will see. Okay, so my talk today is titled Scaling Privacy, Cloud Native MPC, Data Anonymization, and the Path to Open Linux Ecosystem. In this talk, I will explore how we can leverage MPC to enable secure, privacy-preserving data analytics at large scale. Here, I will look at how cloud-native technologies can help us to make MPC practical for real-world application. Also, I will discuss the role of MPC in data anonymization and when we consider GDPR. And also, at the end, I have some updated news for our vision for an open source ecosystem. So as already Christian told, I'm Hossein Yalame. I'm a research engineer at Bosch Research. I'm focused on privacy, preserving computation, and especially secure AI technologies. I completed my PhD in crypto into Darmstadt, December 2023, and officially September 2024, where I work extensively on MPC. And also, I'm trying to make cryptographic techniques practical for real-world applications. If you're interested in my research, feel free to connect me on LinkedIn. So today, I will talk about privacy-preserving computing technologies, and then why we need cloud-native technologies, and why we need some open source, and why we are aiming for open sourcing in Bosch. And then I will talk about some overview regarding Carbon Stack, how we bring MPC to the cloud and how we can use Carbon Stack. Then I will talk about some high-level services using Carbon Stack like Nettle framework for private-related learning, and also privacy preserving people analytics, and also our legal expert there, what will happen if we use MPC considering GDPR. And at the end, I will talk about our donation to Europe Linux Foundation for our Carbon Stack. Perfect. So let's start with privacy-preserving computing technologies. What's that? So what is exactly privacy-preserving computing technologies? I will call it PPCT during this talk. So think of PPCT as a sealed computing environments. They allow us to process data while keeping it confidential, intact, and also under control. For confidentiality, what we mean, we need like data remains protected from unauthorized extraction, meaning even those processing, they cannot access to new information. We always have confidential data here. And we have integrity. We can ensure data is not tampered with during computation. And also we have also control access here. Data can only be processed by authorized algorithms. That's the goal of PPCT. And so, as we know in these days, the data privacy regulation are evolving rapidly, and in businesses, we should adapt to them. For example, GDPR-like regulation are being enforced across major markets. And at the moment, 71% of countries, they already have data protection laws. And we have also more on the way. So for that reason, the global companies need a cross-regularity to just operate smoothly across different countries. And here, what's the goal? Our goal is to use PPCT, privacy-preserving computation technologies, to help to not have any problem with these regulations. So in short, I would say PPCT are not just about security, they are essential for compliance, trust, and secure collaborations in this increasingly regulated world, which at the end of the talk, I will talk about, do we have really compliance? Then we will see. Okay, so when I was talking about the privacy-preserving technologies, I generally have two main approaches. The first approach is like computing on encrypted data, or we name it COED. This includes multi-party computation, or short MPC, or home of encryption, which here we allow computation to be performed directly on direct encrypted data. And here, Carbon Stack is focused mainly here for this kind of technologies. We also can have confidential computing, which relies on secure hardware enclaves like Intel SGX. And here we create a protected execution environment. And while it provides a strong isolation, but it requires trusted hardware and may have limitation in certain applications. So at Bosch, we are exploring various privacy-enhancing technologies, but in this talk, I will focus on computing on encrypted data technology, and particularly using that for privacy, preserving people analytics, and also federated learning. And also, I will talk about the hybrid world of confidential computing and MPC together to have better performance, which it will come later. So what we have at Bosch at the moment, we are exploring a broad range of privacy preserving use cases. However, in this talk, I will highlight two key internal priorities first. The first one is about people analytics, which we are focusing on compliance. Here we use privacy preserving technologies to securely analyze and benchmark human resources, because at Bosch we have more than 400 subsidiaries in more than 60 countries. So we need some data protection and compliance with privacy regulations, which we want to see how we can use MPC to resolve these issues. And also the other use case, internal use case in Bosch is like collaboration focus. We are working on federated learning. Here we enable privacy preserving AI model training across multiple parties. We combine low quality training models while also preventing data exposure. And this is particularly useful for cooperative setting where the businesses can collaborate and also maintain data privacy. And while these are our internal focus area, we are also working with partners to explore additional use cases. For example, if we use this kind of technology, we can have like virtual data pooling. That means we can enable computation on distributed data set without moving or exposing the raw data. And this is really critical for cross-silo analytics and also synthetic data generation. We can also have like secret management, like distribute sensitive data cryptographically, so it can also be processed without being reconstructed in a single location. We can also go for private correlation, which we can allow organization to compute insight across sensitive data set without violating privacy. And this is key for supply chain risk analysis and cyber threat intelligence between different parties. And as also mentioned, we can also use our faulting for collaborative learning, which we don't have a single aggregator. We have different parties which they want to do like peer-to-peer training. We can also use Carbon Stack there and or MPC technology there. So far we talk about why MPC, why privacy preserving computation, and now why cloud native technology? As we know, to scale privacy preserving computation, we need cloud native technology. But the question is why? Cloud native architecture allows us to build a scalable, resilient, and manageable systems. They work across public, private, and also hybrid clouds, which they can enable dynamic and distributed application, which is exactly what we need for privacy preserving data processing at a scale. That's the only way we can achieve. So Carbon Stack embrace these technologies to make MPC cloud native. And by doing that, we want to ensure performance, flexibility, and real-world adoption for Carbon Stack. And why we are considering open source? I would say we have 4 key reasons. First of all, we want to reduce cost and share risk. As we know, developing secure computation is a massive effort. So open collaboration, they can help us to share the burden with companies, institutions, and individuals. That's the main reason. The second reason, we want to improve quality, because the community expertise can allow us to solve problem better and safe and faster, and we can ensuring higher quality implementation. The third thing is we want to increase trust, because as we know, transparency builds trust. So by having open source solution, we can prove their security through some public committee. We can make them more reliable and auditable, because everything is open source there. And the last thing is we want to boost Bosch brand. We want to contribute to open source project, reinforce Bosch reputation, and also attracting talent and strategic partnerships. And also, there is also one proverb which it says, if you want to go fast, go alone. But if you want to go far, go together. And that's why we are building Carbon Stack as an open source system. So what is Carbon Stack exactly? Let's have some overview of Carbon Stack, some short overview. In Carbon Stack, as I mentioned, is about bringing MPC to the cloud. We want to make it practical, scalable, and somehow enterprise ready. So in Carbon Stack, we use cloud native technologies, which will provide enterprise-grade infrastructure for scalability, orchestration, and automation. That's the first part. The second part, we have MPC here. By using MPC, we ensure that data remain encrypted at all times, secret shared encrypted. And the Carbon Stack combines both, creating an open source cloud native MPC for secure data processing. So what that means? This means organization now can leverage MPC as a service. I can call it MPC AAS. But by using Carbon Stack, it can be efficient, manageable, and ready for real-world deployment. So let's see what is our key design choices. For topology, here we work with 2 or more virtual cloud providers. We name it VCPs, which we allow peer-to-peer computation or outsourcing scenario. We also support dynamic client participants and also resource-constrained devices. For Terrace model, at the moment, the main focus is on active security and also malicious majority. That's our main Terrace model today, but we are also working with partners to integrate additional Terrace models, making it more adaptable to different MPC runtimes. So we can be really flexible for all MPC backends, from honest majority, for dishonest majority, semi-honest, or active security. And also our execution model, we support offline, online phase. We do some pre-processing phase. Why? Because we want to make it highly efficient for real-world applications. And by using that, we can have all expensive operations in offline phase, and then we can have really efficient online phase. That's our design choices. And also Carbon Stack is built as a modular ecosystem. We have different building blocks. The first one is utility services. We have Kilishko and Timus here. Kilishko handles correlated randomness generation, which is the key component for secure computation. And we also have Timus, which is our cloud native IAM, or identity and access management solution. We also have some service for data stores, Amphora and Castor. Amphora acts as a secret shared object store for encrypted data, and Castor provides a correlated randomness store. And we also have computing layer. We name it Ephemeral, is an MPC-based foundation as a service. Then using these services, using these building blocks, we can have also application verticals, which we can enable data analytics, federated learning, and in these days, hype AI. We can have private AI also. So as you can see in this slide, that's a high-level view of Carbon Stack is structured and how it supports different applications. We have application layer, which we can enable different solutions like human resources, healthcare, connected industry, and automotive, which they should handle highly sensitive data. And then we have MPC-specific functionality, is like or higher level service like data analysis and federated learning, which there they leverage Carbon Stack foundation services, which provide the core cryptographic and secure computation capabilities. And at the bottom, we also have Cloud Native Foundation, which is built on Kubernetes, Knative, and ensuring scalability, orchestration, and secure service communication. That's whole architecture for Carbon Stack. And how it works exactly. So here we have 4 steps to use Carbon Stack. First of all, we should establish a virtual cloud. Here, multiple virtual cloud providers connect, and they forming an environment for secure computation. And then in the next step, we need to generate correlated randomness. So here again, the VCPs, they pre-compute randomness using secure cryptographic primitives or using confidential computing, which I will explain next slide. And then we have like some correlated randomness to be ready to be used in next steps. And then in the next one, we need client registration and service invocation. What that means the client register and authenticate with VCPs to upload and download data to secure computation. The VCPs now process encrypted data using lightweight cryptographic in online phase. That was our working principle. So as I mentioned, for offline phase, for pre-processing phase, we can have different approach. It could be cryptographic, or it could be like based on confidential computing, which I will explain now. What is our option? The first option is like fake offline phase. That's the baseline. There is no security there. It's just used for development only with no security guarantees. The second approach and third approach is based on somewhat homomorphic encryption. It's like high gear and low gear. But the cryptographic approach, they are really cool. We don't have any security issues, but they are expensive. For that reason, we can also use confidential computing for generating randomness. The one approach is like per-party TE confidential computing protected offline phase, which is based on TEs and also is like having that fake offline phase inside of TE. We can also have different approach here. We can use single multi-TE protected offline phase. That means instead of having one TE, we can have multiple TE, which they talk together, and then they generate the randomness for us. We want to have like better security compared to single TEs. And also we can have Solentium, which we also have in Carbon Stack, is like based on PCGs. That's the recent cryptographic protocols, which we can have efficient pseudo-random correlation generator, and then we can have efficient offline phase. So in Carbon Stack, we are looking for middle ground. As I mentioned, we can have like confidential computing protected or cryptographic offline phase. As I mentioned, in cryptographic offline phase, we have a strong security, but at higher computation cost. For the first approach, for confidential computing, we can provide some level of protection, but still we don't have that fully cryptographic offline phase, and we cannot say, yeah, this is really secure. So for that reason, we can have different approach. As I mentioned, we can even have like single TE offline phase. That means we have just one TE if we do all offline phase, or we can have like single multi-TE offline phase. It's like we have multiple TEs which they do the randomness generation. And we also can have even better architecture like per party multi-TE offline phase. So what's the goal here? We want to have the middle ground. I mean that per party multi-TEs to provide some flexibility based on the risk and resource constraint, and also having like good trade-off between cryptographic approach and TED approach. Perfect. So what we have for offline phase currently, in addition to the cryptographic protocols, we also utilize SGX-based TEs to execute the offline phase. And what is our approach exactly? We integrate MPS speeds to act as a deterministic trust dealer, removing the need for that external randomness sources. And that's the first idea. And then we also considering that per party multi-TEs. And how it works exactly, we have some mutual attestation which we ensure only authorized instance communicate together. Then we have like RA TLS protocol which we ensure key exchange, and then we just generate the random numbers, and then we can just use it in the system. So by doing that, we can have like massive performance gain compared to pure cryptographic approach. We can have order of magnitude faster correlated randomness generation. We can have minimal communication overhead, and just for we also have security trade-off. If we need some good performance, we should use this approach for offline phase. But if we need pure crypto solution, we should use that cryptographic based offline phase. And I would say this is not just theoretical, and CDGP from India is actively implementing this concept based on our research. That's a good thing about open source. We can have different collaborators. So how it works exactly? Consider you have a company, now how it works to using Carbon Stack. So first of all, we need to secure some setup for our Carbon Stack. For example, the collaborators, the companies can create an encrypted cloud using cryptographic protocols. And then in next step, we do some data injection. It's like the parties inject their data to our encrypted cloud without actually sharing it. And then they also define a data access policy and some agreement on computation. And at the third step, we can just do distributed secure computation, which the computation is distributed across multiple parties, no party sees raw data or intermediate result. And at the end, the final computation are reviewed only according to the predefined access policy. So here, now the companies, collaborators can use our cloud native technology, Carbon Stack. So what's next now? Perfect, we have Carbon Stack Foundation service, that's cool. And where do we go from here now? So here, as I mentioned, we have a strong foundation Carbon Stack, but the real value comes from building higher level services. So in next step, we expand Carbon Stack with advanced services. We consider federated learning to use Carbon Stack to provide privacy for federated learning training, and also for data analytics, which we have like query secret share database using SQL to see if we can really use Carbon Stack there, and then also we also did some legal analysis. If we use or human resource analytics using Carbon Stack, do we need to care about GDPR, or we have a good solution, which I will come to that at the end. So the first service is our Nettle. Nettle is privacy preserving federated learning. What is the key idea here? So I think all of us know what is federated learning. We have different clients. They do the local model training. They will share that local model with some server. The server will do the aggregation. They will send it back to the clients, and they will go the next round to have at the end a good global model. The first idea of Nettle is separation of concern by role segregation along asset ownership. What that means, here we have a key problem for federated learning. We have centralized servers which they create a bottleneck for trust and data security in FL. And what is the solution in Nettle? We decomposing the system into subsystems and roles to distribute ownership of valuable assets. We have different stakeholders and different roles in Nettle. We can have data owners, which they hold and process sensitive data locally. We can have clients, which they train model on local data without exposing it. We don't have any central server. We eliminate a single point of control. We have some model owner, which they maintain and updates the global model. You also have some orchestrator, which they manage communication workflow. And also some role with aggregator, which they compute global updates from local models. And why this matters? Because by this separation, we can reduce the risk of trust issues in centralized FL. We can enhance data security by eliminating server control, and we can also ensure ownership clarity between different roles. Sounds good. But still, we have some challenges with classical FL. I would say we have some privacy vulnerabilities still in FL, and FL is not private yet. Why? Because we can have different attack on client or aggregator side. In client side, we can have reverse aggregation attack. For example, consider like we have a group of clients, and we can name it group A from one country and group of clients, group B for another country. Now we can consider these groups as a two client setup. So client A, it can subtract its gradient from the global model. Then this isolates client B gradients. So it's exposing its updates. And what is the impact? It can break data confidentiality by leaking client B information. So why it happens? Because intermediate intermediate model or the global model is revealed to the client or for in FL. So we need also protect the privacy in client side. That's one thing. The second attack is like aggregator side attack, because the aggregator can do gradient analysis, and the aggregator inspect gradient to infer feature of training data. It can reconstruct sensitive information like images, text patterns, and it can do gradient inversion. It can use model architecture, and it can use gradient to reconstruct original training data. And what is the impact? It can reveal private training data to the aggregator. So we can have attack in both sides. So we have some problem. We have some privacy issues here. And also in this slide, we can see attack methods are advancing rapidly. And here the fidelity of gradient inversion attacks has dramatically improved from 2019 to 2024. And now the attackers can reconstruct highly detailed image from gradient. So you can say, for example, in 2019, it was just noisy, low quality reconstruction. 1 year later is that slightly improved details, but still blurry. 2021, they have like more refined object shape start to emerge here. And now in 2024 and 2025, we have near perfect reconstruction. We can reveal sensitive training data. So what we can say, what's the conclusion? FO without additional privacy is highly vulnerable. So how do we defend against these evolving threats, evolving attacks? That's the second approach. The second idea of NETL. We protect at every level. What we did exactly. So we consider multiple levels and we use the most feasible privacy enhanced technologies. Here we have different levels. We have the data plane, we have control plane and model plane. So for control plane, we can just use some remote attestation for integrity enforcement. That's the solution is there. But for data plane and model plane, we should see which kind of technology we can use. But consider that training data by data owner. One solution is like using MPC there. That means we need like model training for clients based on MPC. But unfortunately, is not yet efficient. So here we decided to use TEs on client side. That means we are doing local training on client side. Local training using TE on client side. But for model plane, for model owners, for doing aggregation, we can use MPC because we use aggregator side, we use MPC for model plane, and for attack on client side, we use TEs. So let's see how it works exactly. Okay, so here you will see what will happen if we put all together. We have data owners, aggregator, model owner, and orchestrator. Let's see how it works exactly. First of all, here, the model owner uploads secret shade weights to aggregator and inject experiment strategy, the initial model secret ID, and also we have all of them after orchestrator doing some verification, integrity verification with remote attestation. That's the first step. Then the client registered with orchestrator and they are permitted to do experiment again after that integrity verification via remote attestation. And next step, the orchestrator select run participants from the set of permitted clients. They choose parameter based on experiment and also triggers the training run. And now the client download the current model from aggregator and they use secret ID received from the orchestrator. So now the client can perform training on their local data. And after that, they will upload the secret shade model to the aggregator and transmit the secret ID also to orchestrator. And here we use TEs to do the training on client side. We can also use MPC, but as I mentioned, it's expensive at the moment. But hopefully in the future, maybe MPC also feasible for training. And next step, the orchestrator triggered the MPC-based secret aggregation, which here we use Carbon stack. We do the aggregation in private manner because we don't want to have any attacker on aggregator side, any chancer. And then the orchestrator launched the next training round or send back the ID of secret containing of the global model to the model owner. And the model owner now fetch the final model, and then it can see, yeah, that's the global model, cool. We train the model without any privacy issues using MPC on aggregator side and using TEs for client side. So far, it was about federated learning and or NETL framework based on Carbon stack. The second or internal priority in Bosch is like privacy, preserving people analytics. Let's see what that means exactly. So here in the company, we have really customer pain at human resources. We have a problem which we have human resource data, which is fragmented across 400, more than 470 subsidiaries in 60 countries, which we have like high friction due to regularity and IT complexity. And also we need some pooling data, because by pooling data of different subsidiaries, we can enable better statistics, better AI and analytics, but we have privacy concern and it prevents direct sharing. So what's the goal? We want to achieve the best solution and having the pooling data without caring about the problems, without not caring with a good solution for privacy concerns. We want to ensure data privacy when we also put in the data. So if we pull the data, we have a lot of risk. For example, we have data breaches because we need like handling hundreds of thousands of sensitive records. We have some conflict in interest because we involve different companies, worker council, employees, and DSOs, which that make agreement for pulling data difficult. And also we have heterogeneous regulation. As a company in different countries, we should have a compliance with GDPR, CCPA, APPI, PAPA, and also it's adding operational burden for us at the moment. But the good thing is we have the solution. We can use Carbon Stack virtual clouds. It will enable privacy preserving people analytics. And then the different subsidiaries can use this technique. How it works? The data is encrypted locally before leaving the subsidiaries, so all fine. It's just encrypted data. Then we use MPC, which no single party can see raw data. And then after having the analysis, they can encrypt it only by authorized parties. And what is the key benefit? Here is like, we have like mathematical privacy guarantees, which we enable global HR analytics without compromising sensitive employee data. Cool. That's due to MPC and thanks to MPC, I would say. So what is the key benefits again? Using Carbon Stack, we have lower risk of data breach. Perfect. We have peace of mind for a stakeholder. Share your data. We will do analysis. All fine. We have mathematical guarantee here. Again, perfect. And we have some baseline for compliance for different regulation rules, which at the end of these slides, I will talk about also the legal experts' opinion. Yeah, what will happen if you use MPC considering GDPR? But before to go in that, let's talk about the technical solution, which we just discussed for people analytics. So here we have different parties. We have input parties. They are our different subsidiaries in Bosch. We have computing parties, which is our VCPs for Carbon Stack. And we have the output parties, which they are like data analysis, which they want to ask some query. For example, I have this query. I want to have some group by join query over the subsidiaries data sets. So here the data analysis send the SQL query to Carbon Stack. Then the input parties, the data owners, secret share their data with Carbon Stack VCPs. And Carbon Stack, we use MPC to doing the analysis. And then we have the output, which we will send the output to reconstruction by data analysis. So that's the technical solution. Perfect. So now the time is for the legal perspective. What will happen if we use privacy preserving people analytics? Do we need to care about GDPR? Do we have a good solution? Do we have anonymization? Which I will explain now. So first of all, I want to have some disclaimer here that this assessment is part of a publicly funded research project. And we at Bosch, we contributed to technical use case. It's like, what is MPC? How we can use MPC? How we can use carbon stack? And from Munster University, Professor Hogan, they contributed to the legal assessment. And I should say, the technical solution is not implemented at Bosch. And also, this legal assessment is an independent academic study. And there's no endorsement. Considering GDPR, we have some legal challenges in people analytics. We have this data protection fundamental, which we have like really a strict requirement for processing employee data. So what is the key legal challenges here? The first one is like processing of sensitive personal data, Article 9 of GDPR. If you consider like processing some sensitive data for your HR use case, like health data, like sick days, or trade union membership, you have this legal challenge here. The next one could be like group-specific challenges. No privilege for data exchange with corporate groups. And the GDPR requires subsidiaries to be independent entities, and also complex responsibility structure within corporation we need for GDPR. And the third one is like international dimension. As I mentioned, we are like 470 subsidiaries in more than 60 countries. So we have like cross-border and third country data transfer, and which is different in national data protection laws. And also, the last challenge is like general requirement for employee data processing. We need some legal basis for processing, Article 6 and 9, or we need some risk-based approach for security of data processing. And also we need like data minimization and purpose limitation and transparency when we care about GDPR and when we consider GDPR. So that's the legal challenges. So now let's see what was the traditional anonymization, and then what will happen if we use MPC approach. So in traditional anonymization, they rely on removing or modifying some attributes, but this approach has some disadvantage, because we can have some impact on data utility. By using that, we will have like significant loss of data precision. We will reduce analytical capabilities, and also it's like always that's inherent trade-off between privacy and data utility. If we have a lot of modifying, then we will lose that data utility. And also the risk assessment here is like, is only limited protection, and it cannot really work for advanced attacks, like considering attacks for AI or big data techniques. And also traditional anonymization, we have just a static security level, which it does not adapt to changing security threats. But for MPC, if you consider MPC, we offer a fundamentally different approach by preserving data integrity while also ensuring mathematical security guarantees. And here we have anonymization through fragmentation. So data remains intact, but is encrypted via secret sharing. We have fully distributed computation, eliminating central trust points. We have flexible adoption to new processing requests. We can have full analytical capabilities, and also our privacy control are adaptive. We can also respond to dynamically to security threats. And also our risk assessment, we have like distributed security model. We ensure it mathematics, as I mentioned. We also have protection against collusion, and also we can have adaptive security levels. Okay, cool. So let's see if we can consider MPC as a anonymization when we're talking about GDPR. So when discussing anonymization, we must distinguish between two fundamental approaches. The first approach is like traditional view, is like absolute or objective approach, and the second one, relative approach. For absolute approach, when can data be assumed to anonymize? So that requires the absolute impossibility of re-identification. We should count for the total sum of human knowledge when determining risk. And here, data is either anonymous or personally identifiable information. There is no middle ground. And in the age of big data and AI, achieving true anonymization is nearly impossible. And also, we don't know what others might know in the future. And also, by using this absolute approach, we block real-time and useful data application due to that rigid classification. But if we consider a more practical alternative, so when can data be assumed to anonymous for relative approach? We use a risk-based assessment for re-identification potential. Here, the practical feasibility matters. And GDPR Recital 26 consider only all means reasonably likely to be used for re-identification. And here, the same data set can be anonymous for one entity, but PII for another. That's cool. It's like MPC. My private input for me is like the good input, for the other parties like PII. So this approach, the good news, is already supported by European Court of Justice and European General Court. And it's also backed by legal ruling like ECJ earlier case. And also this third-party re-identification capabilities are irrelevant, and if they are not reasonably accessible. If you don't have that reasonably accessible, so it's not relevant for us. Also, that anonymization via pseudonymization is recognized as a valid approach for relative approach. So what this matters for MPC? So MPC aligns well with this modern legal framework. So that make it promising solution for privacy preserving computation, because for relative approach, we have our solution, MPC. So here,
Hossein, you have like 2-3 minutes left.
I have what?
You have like 2 or 3 minutes left.
I combine my both tags. It's invited tag, contributed tag. Yeah? Or should I? Let's both tag together, right?
I'm not aware of that, but I assume it's fine.
Should I continue or?
No, I got confirmation. It's fine. Continue, please.
Okay, perfect. Thank you. So here we examine the legal implication of MPC, and we can see, can we consider anonymous using MPC under GDPR? The lawyer told the key distinction here lies in who controls the secret share, a single entity or independent legal entities. So if we have single legal entity which controls the shares, the bad thing is like there is no anonymizing effect because the entity holding all shares, so it retains access to the original data. And here, the secret sharing is ineffective because all shares are under control of a single entity. So the control entity can easily reconstruct the data and re-identify individuals. The result was data remains subject to GDPR regulation. It is not truly anonymous. So if you have an MPC framework, you can say, yeah, I will use a single machine just for my computing parties. Then you cannot say you're not subject to GDPR. So, but if you consider independent legal entities, which they control the share, and now anonymous data processing is possible. And here, the collusion is legally prohibited due to legal autonomy of group entities and also management obligation to comply with the law. And the result, it was also good result. Data processing is not subject to GDPR as no single entity can reconstruct the data. What was the key result here? For MPC to deliver on its promise, the legal entity separation is critical. If shares are held by independent legal entities, the data can be considered anonymous. So we can bypass GDPR restriction. Good for MPC. So somehow we can say MPC can be a game changer, because in traditional data processing, we involve some storing and processing personal data in plain text, which make to subject to GDPR. So without MPC, we have input data, which they contain personally identified information, and everything is in plain text. For output data, if the output still contain PII, it remains subject to GDPR. But if anonymized through other means, it may be exempt from GDPR. But by using MPC, we have kind of paradigm shift. The data is first secret share, ensuring no single entity has access to complete personal information. And we use processing using MPC, and also the output data can also remain anonymous and avoiding GDPR obligations. So here, by using MPC, we can eliminate data processing obligation under GDPR. That's a good thing. And that enable global analytics without regularity burden. That was the last sentence of the assessment. Cool. So far, I talk about, yeah, MPC is magic, MPC is good. We have carbon stack based on MPC. We have different application, higher level services. So it's now, I would say, the time is now. So we are ready to go for some MPC ecosystem, an open source MPC ecosystem. So what is the vision? We want to have like a future-proof MPC ecosystem. As we know, MPC is evolving, but current solutions are mostly proprietary. And also, we need an open ecosystem based on open standard and open source technology. And that's the reason we're trying to driving this shift to enterprise grade and also trustworthy MPC solutions. And for open MPC with Carbon Stack, we have some future to be open, to incorrect network effect, and to have some standardization. We want to be transparent. And this approach enable collaboration between industry leaders and also academics. And so far for Carbon Stack, we have some collaborators from Cybernetica, Resolve, SAP, Honda, and Data for Public Good from India, and also some academics like UTS from Sydney. Okay, so let's see what was the history. In 2017, the Carbon Stack project started as an internal project for some internal use case. But in 2021, Bosch decided to have Carbon Stack open source because of the reason which I mentioned at the beginning. And then, at the end of 2021, they started to build community from Honda, SAP, and then recently from India, Resolve, and Cybernetica. That was until November 2024. In December 2024, we decided to donate Carbon Stack to open source foundation like Europe Linux Foundation. And now we want to reach to our goal, open MPC ecosystem. So what was the past? The past, as I mentioned, we started with internal project. It was just a cloud initiative by Bosch. Then we just considered developing privacy, preserving computing for secure data sharing. Then we went for open sourcing to have like external interest and industry needs, and then increase transparency. Also, as I mentioned, position Bosch as a key player there. We also have something like the first archetype, and on that time, the collaborator was mainly by academia and also that Cryptex public funded project. And then after that, after 2021, as I mentioned, in 2024, December, we decided to go for our vision. And now we have donation into Linux Foundation. And now we want to go for more open and community-driven ecosystem. We want to have amplify external collaboration. We want to engage with new partner, industry, and developers. And we want to shift from Bosch-driven initiative to a multi-stakeholder platform. And we want to go for multi-vendor infrastructure. So now that's the time. Today, we are in this step. We donate to Linux Foundation. And what we want to do, we want to have like improved technical basis. We want to have like community-driven enhancement and new feature to Carbon Stack. We want to have a better value proposition. We want to have more use cases and standardization and also real-world deployment. We want to have more MPC adapters, which is increased demand for privacy, preserving computation. And we want to strengthen the developer base and expanding integration partners. And at the future, it will be like a self-sustaining cycle. As more contributors join, the technology improves. A better platform attracts more adapters, the more real use cases, a stronger ecosystem, and long-term visibility. So the Carbon Stack journey now continues with open source collaboration, and we want to ensure privacy enhanced computing for all people. So if you're interested to join, feel free to join us, because we want to make MPC great again, I would say. So the summary of my talk, I talk about privacy, preserving computation technologies, which they are on the rise now. We have huge business impact and risk mitigation potential here. And that's also especially relevant for advanced data analytics and also predictive learning. And we use secure multi-party computation as a solution. We enable end-to-end encrypted data processing. We also ensure a strong security guarantee for business, like our HR use case here. And the unique advantage of Carbon Stack was like we bring MPC into cloud, and also we enable cloud native privacy preserving computation. And our mission was like setting the standard for enterprise MPC, and also we established Carbon Stack as a de facto open source solution. And at the moment, we support also higher level services like data analytics, predictive learning, and because of our foundation, you can also consider all privacy preserving computing. And as I mentioned, from December last year, we have a new chapter. We did the donation to Linux Foundation at Europe, and we are doing transition in Carbon Stack into the open source community. We are improving collaboration and industry adoption. We are trying to driving new innovation in privacy preserving computing. And I would say here, thanks for your, wait, it doesn't work. Okay, thanks for your listening to my talk. I'm here if you have any question. And my last sentence, the community of TPMPC and MPC is like, let's shape the future of privacy preserving computation together. Thank you.
Thank you, Hossein. The audience is clapping. Thanks for the great presentation. Now it's time for questions. Any questions to Hossein? Here in front.
Yeah, that was a very nice talk, Hossein. Thank you. Do you have any plans to integrate other PETs, privacy enhancing technologies, or as you call it, PPCTs, like homomorphic encryption, zero knowledge proofs into your Carbon stack framework?
Yeah, currently, thanks for the question. Currently, we are just working on MPC for Carbon stack, but also in Bosch, we also have different other technologies in different activities. But for Carbon stack, at the moment, the main focus is just MPC. But for something like ZKP, we didn't decide yet. But yeah, our plan is like being quite flexible, because that's the goal of going for also Linux Foundation, because then the partner can join there. They can say, yeah, for example, we need ZKP here. So we can say, yeah, feel free to add it. But for our plan, just MPC at the moment. But for different model, we are working on it, because currently we have like malicious security and also dishonest majority, but we also have plan to work considering something like ABY2, because the function dependent preprocessing, which we can have like efficient online phase for some application like PPML, and also with a partner with like from India, CDGP, if I'm not wrong, they also work on offline phase, for example, which we want to try to extend the MPC families there, but now just MPC.
Thank you. More questions? While we're waiting for more questions, maybe I'll ask one. So personally, I know Bosch as a company producing like household appliances like washing machines and ovens and so on. Like, can you give some examples of real-world use cases where you imagine to deploy this cloud-native infrastructure? Like, which kind of data you will collecting and processing?
Yeah, at the moment we use it for our internal use case. For example, as I mentioned, for Bosch, for that or human resource analytics, for example, we want to do some ML analysis. We cannot do that at the moment because we have subsidiaries in more than 70 countries, more than 60 countries. And everyone, they have their own law regulation, they have some privacy issues. Or we are caring about privacy, use our Carbon stack and do the analysis there for internal use case. But in the future, because in Bosch research, we are aiming to have like some solution for the future. For example, if you consider like some hospitals, which they wanna do some better global model training, because if you have more data, you will have better model. But currently they cannot do that because that patient data is like really sensitive data. So we need some solution there. So by using like our FL framework or Nettle, the hospital can do the local training. It could be based on TE or plaintext is on a hospital. And then they can use Carbon stack for global model training. Then they have that better model training and they can have better treatment for their patients.
Right,
and the other thing could be like, for example, it can use also for, in these days, the hype of chatbots. For example, you ask something from the chatbots, you reveal anything to them. Yeah, that's my name, that's my birthday. Yeah, what do you think? Yeah, then there's some privacy issue also here. Maybe in the future we can also use some kind of techniques also for this kind of application.
Thank you.
And the last application which I can mention, like as you also heard about that, I think it was Bybit, if I'm not wrong, the company which they lost like 2 billion of Ethereum in blockchain, and the main reason was that their key management, it wasn't based on cryptography techniques. So for that reason, they lost a lot of money. So hopefully by using MPC, by having more people, we can provide private word. Hopefully.
Thank you. More questions to Hossein? Maybe I'll ask another cheeky question. So I remember a TPMPC talk by Sven like 1 or 2 years ago where he said you are planning to replace MP Speeds as the core MPC engine with a more like enterprise grade re-implementation. So what's the current status of that approach?
What was the question, Christian? I didn't get it.
Previously, you said you wanted to replace MP Speeds with like an enterprise-grade MPC implementation. Are you still actively working on that, or is MP Speeds like the future?
Yeah, at the moment, our backend is just MPS Speeds. But again, in that community build link, we want to also change our backend. But at the moment, now the status is like the backend of MPS Speeds only.
All right, thank you.
No problem.
If there are no more questions, I would say let's thank Hossein again. I think most invited speakers get a small gift package. Maybe I can take it to you in Darmstadt, like maybe next Saturday or so. But yeah, you will get it. All right. With that, I think there's a second talk in the session by Amit on secure sorting, if you want to come in front and set up.
Hi everyone. So today I'll present this work on secure sorting and selection via function secret sharing. And this is joint work with my collaborators Elliot Boyle, Nishant Chandran, Niv Gilboa, Divya Gupta, Yuval Ishai, Mahimna Kelkar, and Yiping Mao. So we all know by now what MPC is, so I'll not go into the details. Parties have private inputs and want to securely compute some function on their private inputs. Usually we have two types of adversaries, semi-honest and malicious. For this talk, we'll restrict our attention to semi-honest adversaries. And the efficiency metrics that we would like to consider is local computation, communication, and rounds. And we assume that parties are connected by peer-to-peer, P2P synchronous channels. Okay, so a popular paradigm in MPC is this offline-online setting, also known as the pre-processing model, where the protocol is divided into two stages, the offline phase and where parties produce some correlated randomness, and the online phase where parties consume this correlated randomness to securely compute the function on their private inputs. Why do we care about this offline-online paradigm? Is because it helps us reduce the online cost, and in practical settings, online cost captures the response time of our protocol once the input arrives. Okay, so what is the secure sorting problem? So we have a list of n values, x1 up till xn. And these values are additively shared between parties. Parties interact in the end, they output a secret share of values with y1 up till yn, such that y1 up till yn is the sorted version of their original inputs, x1 up till xn. And the setting we consider is this three-party setting where we have three parties. And we also consider a special case of this three-party setting, also known as the 2+1 party setting, where one of the parties only speaks during the offline phase, and the other two parties only speak during the online phase. In both cases, we consider that the adversary can corrupt any one of the parties. And we assume that the inputs and outputs of the sorting have to be additively shared between two of the parties. So in this setting, we aim to minimize the online communication and rounds of the secure sorting protocol while having a practically feasible offline phase. And we only focus on solutions which use lightweight symmetric key primitives. So let's look at what prior works are in this area and what our result is. So we see that all prior works are online inefficient in terms of communication. So let's say n is the number of items that we want to sort, and L is the bit length of the items. So prior works either have constant online rounds and high online communication. For example, if you take a garbled circuit-based approach using some sorting circuit, you get 2 online rounds. But now your communication is high in the sense that you have this lambda factor blow up. Well, lambda is a security parameter, typically 128 in practice. Or you have low online communication but non-constant rounds. So for example, if you do a radix sort, a GMW style radix sort approach, you get decent online communication, but your rounds are now not constant. So our goal is to get constant online rounds and linear online communication, linear in N and L. So for example, a question is, can we get 2 online rounds and order NL communication? And in this work, we show that using function secret sharing for the class of point and comparison functions, you can get sorting protocols with constant online rounds and linear online communication, and the constants are pretty small. Okay, so let's go into how this works. So before that, I'll cover some high-level prelims. So let's say this bracket notation of x denotes additive sharing of some value x. Given such a sharing, you can do some operations on it, for example, addition. And this doesn't require any interaction or pre-processing. So you can add, given sharing of 2 inputs x and y, you can add them up to get a sharing of the sum of the inputs. You can also do a multiplication on shared values. This requires an online interaction of 1 round and communication which is proportional to the input size. The pre-processing that you need here is beaver triples. You can also do more sophisticated stuff such as comparisons on secret shared values. This also requires 1 online round and communication proportional to the input size using pre-processing called distributed comparison function. What you can also do is, if you have an input x, you can convert it into its 1 hot vector representation. This again requires 1 online round and communication proportional to the input size. And the pre-processing that you need here is so-called distributed point function. And these 2 kinds of pre-processing is what comes under the function secret sharing paradigm. Okay, just to give an example what 1 hot conversion means. So let's say you have some input domain which are integers in the range 1 to 5, and the input is 3. Then the 1 hot vector representation of this input 3 is a vector of length 5 over. So the length of the vector is equal to the domain size, and it's a unit vector where you have a 1 at the 3rd location and 0 everywhere else. So this is the 1 hot vector representation of the input 3 over the domain 1 to 5. And this single round of communication that is required in all these 3 gates, multiplication and comparison and 1 hot conversion, is basically where you just reconstruct a masked version of the input. Okay, so our high-level approach for this secure sorting problem is the following. So to sort a list of shared values x1 up till xn, we divide it into 2 phases. The first phase is secure ranking, where we take the inputs x1 up till xn and compute ranks R1 up till Rn of these inputs. What is rank? The rank Ri of an input xi denotes how many elements are less than this input xi. So once you derive the ranks, you use these ranks to reorder the inputs, and this is what's called secure routing. So once you have the secret shared ranks, you reorder your secret shared inputs to get the sorted output. Okay, let's take an example. So let's say you have 3 inputs, x1, x2, x3 over here. You rank them, so ranking will give you some values. So here the 22 is the smallest element, so it has rank 0. 55 is the largest element, so it has rank 2. So this is what ranking will give you. Once you have the rankings, you can take the rankings and the inputs and reorder your inputs as per their ranks. So the element with the lowest rank, which is rank 0, should go into the first place. The element with the highest rank should go into the last place. And in the secure MPC setting, you do this over secret shared inputs. Okay, so we have these 2 phases, secure ranking and secure routing. And for each of these phases, we have some protocols that we propose in this paper. So for secure ranking, we do a comparison-based ranking based on DCF, and also propose a non-comparison-based ranking based on enhanced form of DPF called multiplicative DPF. We'll see this in next few slides. We also propose, so for routing, there is a well-known approach based on shuffling. This is well-known in literature. We propose an alternative routing protocol based on DPFs that we'll see in the next few slides. And this DPF-based approach has the advantage of cutting down a round of communication compared to the shuffle-based routing approach. Okay, so now let's go into secure ranking. So, so for comparison-based secure ranking that we propose, we basically exploit this so-called aggregation feature of FSS, function secret sharing-based comparison. So earlier in the slides, I mentioned that using function secret sharing, you can construct these comparison gates that let you compare 2 secret shared values. This is based on this distributed comparison function, which is an FSS primitive. So let's say you have n values which are secret shared, x1 up till xn. What you can do is you can use these comparison gates to perform all pairwise comparisons. So all n choose 2 comparisons between all these secret shared inputs. And then you get the secret shared outputs of these comparison results. What you can then do is you can aggregate the results of these comparisons in an appropriate way to compute the ranks of these values x1 up till xn. And the nice thing is this aggregation phase is totally non-interactive. You can do it locally. And we'll see an example in the next slide. The only communication that happens is before you start doing comparisons, where you reconstruct a masked version of the inputs. And this requires linear communication. So let's take an example. Let's say we have 3 inputs, x1, x2, x3. And let's say x2 is greater than x1 and greater than x3. So once you do the comparisons, you get this comparison matrix where each cell indicates whether the left value, the row value is greater than the column value. So you get this comparison matrix. And now to derive the ranks, so if you want the rank of the first element x1, you just add up all the bits in the first row. So the rank of x1 in this case is 1, rank of x2 in this case is 2, and rank of x3 is 0. When you have secret shared inputs, you get secret shared comparison results. And because the rank function is just a linear combination of these secret shared results, you can add these up locally without any interaction. So this was our comparison-based ranking approach. Now we'll see another approach based on, it's a non-comparison-based ranking approach, which has different trade-offs compared to the previous approach. So here, let's say we have n inputs, x1 up till xn, over some domain of integers up from 1 to L. In the first step, what we can do is we can convert these into their one-hot vector representations. So you get n vectors for each input, x1 up till xn. And these vectors are of length L, where L is capital L is the domain size. What you can then do is you can add up all these one-hot vector representations to get an aggregated vector, V. And think of this V as a histogram of the input items over the input domain. After this, you can take a prefix sum to get a final vector W. The observation is, if you look at the ith entry in this vector W, it represents the number of elements which are less than equal to I. This implies that if you want to compute the rank of a particular input xi, it's simply the inner product of W with the unit vector, one-hot vector representation of that element xi, which is ui. Okay, so now let's see this in action. So let's say our domain is integers from 1 to 6, and you have these three inputs, x1, x2, x3. In the first step, you convert them into their one-hot vector representations. So 3 gets converted into this length 6 vector, which has 1 at the third location, and so on. You add these vectors up to get a vector v, and then take a prefix sum over this vector. Now, if you want to compute the rank of x1, you take an inner product of this final vector w with the one-hot vector representation of x1, and the output that you get is 2. Similarly, you can do this for other inputs, and you get the ranks. Okay, so now we want to do this over secret shared inputs, right? So we have secret shared inputs, and you can use these DPF-based one-hot conversion gates that I mentioned earlier to get a secret sharing of their one-hot vector representation. And notice that all the operations that we do in this next couple of steps are linear. You're just adding things up, so these steps can be done easily. In the last step, you have to do this multiplication between two secret shared values. And this requires a secure multiplication, which requires some interaction. And the communication that you require to do the secure multiplication would be equal to the length of the vectors, which is exponential in the bit length of the inputs. And so this is not good for us, because our goal is to get communication which is linear in the input size. So what do we do? So what we do is we use, instead of converting these red shares into instead of getting additive shares of the one-hot vector representation, we convert them into these purple shares. What are these purple shares? These purple shares are replicated secret sharing in a 3-party one-corruption setting. And to get this, we use an enhanced form of DPF called multiplicative DPF that was constructed in one of our earlier works. So replicated secret sharing is also a linear secret sharing scheme. So you can just do all the linear operations as usual. But in this final step, when you want to do a secure multiplication, the observation is that replicated secret sharing allows one level of multiplication without any interaction. So parties can just locally multiply their shares to get an additive sharing of the final rank. So we no longer have that exponential in bit length amount of communication. Okay, so now let me go into the secure routing approach. So as I mentioned, there are two approaches. One is the shuffle-based routing, which is well known in literature. What we do here, what is done here is you start by shuffling your inputs before you rank them. So, and this requires like 2 online rounds and linear online communication. Once you get the ranks on the shuffled values, you can just reveal them. And this is fine because you started by shuffling your inputs. And this requires 1 online round and linear online communication. Once you have revealed the ranks on the shuffled inputs, you can, the routing is simple. You can just reorder the shuffled shared of inputs locally without any interaction. This is shuffle-based routing. Now, next we'll see a form of DPF-based routing, which has the advantage of cutting down a round compared to the shuffle-based approach. Okay, so again, we have a list of items and we have their ranks and we want to route them. So as a first step, what we do is we convert the ranks into their one-hot vector representations by using these one-hot vector gates that I mentioned earlier. So, and then what you can do is you can think of these set of vectors as a permutation matrix. And now you can simply do a multiplication of the input vector with this shared permutation matrix to get the routed output. So this works, but this multiplication would require communication which is order n square. And this is not something that we want. We want linear communication. So to avoid this, what we do is the following. For each input, we sample these masks, which are secret shared between the parties. These masks are S1, S2, S3, for each input, X1, X2, X3. And we do a secure multiplication between the inputs and their masks to get a multiplicatively masked value. And then we can simply reveal this. And when we do the one-hot vector conversion gate, instead of having ones at the non-zero location, we have the inverse of the masks embedded in the non-zero locations. So once we have this, we can do a multiplication of the revealed values and this permutation matrix with these embedded mask inverses to get the final routed output. The masks, as you can see, will cancel each other. And the reason why this avoids this quadratic communication that we had earlier is because we are doing a multiplication between a public vector and a secret shared matrix, which can be done locally. So the only communication that you do here is in doing the multiplication between these two vectors, which has linear communication. Okay, so let's look at our results from an asymptotic viewpoint. So for the baselines, we have a sorting circuit based approach using garbling, which has constant online rounds, but it has this security parameter. Okay, so it's pointing at the wrong location. So in the online communication, you have this lambda factor blow up, which is typically 128 in practice. As another baseline, you have a secure radix sort based approach where your communication is much better than the sorting based, than the garbling based approach. But the downside is that the online round scales with the bit length of your input. So in comparison, like we have these two approaches. So if we use comparison based ranking, for both our comparison and multiplicative DPF based ranking, we have constant online rounds and linear online communication. This does not come for free. So we pay a price in the online computation compared to these prior works. So for online computation measured as the number of PRG calls, you can see that our approach based on comparison based ranking has quadratic in n computation cost. And the approach based on multiplicative DPF based ranking has exponential in bit length amount of computation. And at a very high level, for comparison based ranking, we are doing this all pairwise based comparison, right? So that's why the n square factor is showing up. For the multiplicative DPF based ranking, this 2 power L term shows up because we convert each input into its one hot vector representation, which explodes the communication, sorry, computation. So apart from this, we also have offline communication. So as you can see, like a comparison-based approach has the worst of offline communication among these other works. Multiplicative DPF-based ranking has a offline communication comparable to the sorting-based approach. Slightly better than the sorting-based approach, the garbling-based approach. Okay, so we also explore another direction where we try to reduce the quadratic cost in this comparison-based ranking to something which is sub-quadratic. And this is based on compiling these so-called algorithms in Valiant's model, where you do round-by-round sorting. We show that using FSS, you can compile these algorithms into secure protocols. And the price that you pay is that you have slightly higher constant rounds than the approaches that we discussed. But the benefit that you get is your computation, online computation, and offline communication now is sub-quadratic compared to the naive all pairwise comparison-based approach. Okay, so our improvement is not just asymptotic. In this slide, you can see that the constants are also pretty small for all the metrics that we saw on the previous slide. We also show a barrier result. So you can question whether it's possible to have a one-round sorting protocol. So we also show that if you want to construct an FSS gate for sorting in one round using linear communication, then this implies an FSS scheme for the class of conjunctions on n-bit inputs. And this is known to be a hard open problem. Thanks.
All right, thank you for the great presentation. Any questions for Amit? Yeah?
Hi, thank you for the great talk. I would have two questions, like one short and one a bit longer. First one, it seems like the protocols are designed for fields.
Yep.
So I would be interested if they also are generalizable to rings.
Right, so the multiplicative DPF-based ranking approach that I mentioned, the routing which requires the multiplicative masks, that is based on fields, but the other protocols works on rings. So like, okay, let's go over here. Right. So among these you can make different combinations of ranking and routing. So only the DPF-based routing approach requires fields.
Okay, thank you. Follow up. Did you run any experiments, or did you plan running any experiments? And what exactly would be use cases where this runs well? Because, for example, the radix sort works on really big data sets where usually you get a huge problem also with computation, where here the drawback also might be significant.
Good question. So we did not implement, but we have estimates of the costs for different parameter settings. So I'll show you 3 different parameter settings. So on the right, you can see system parameters. And on the left, you can see input parameters. So let's say you have 1 million input items. And you have small bit length. So in this small bit length, our approach which requires on DPF will work well. So if you see a comparison between the garbing-based approach, radix sort, and our work, so we have very low online communication and low online rounds, in this case 3. In terms of LAN runtime, radix sort is much fast. But in terms of WAN runtime, our approach is much faster. And the reason is when you are over WAN, our protocols are much better in a setting where communication is a bottleneck, because we try to optimize for online communication. So in settings where communication is a bottleneck, for example, WAN, the runtimes of our protocol are much faster. In a setting where computation is a bottleneck, their radix sort approach would be better. So,
okay, that's great. Thank you.
Yeah, there are these other, this is another parameter setting, for example.
Hey, thanks for the talk. Can you briefly describe what a multiplicative DPF is and how do you construct it?
Right, so multiplicative DPF is one which, so in a normal DPF, when you get the outputs are additively shared over some group. In a multiplicative DPF, the outputs are shared as per a replicated secret sharing scheme. So in our setting, what we use is a 3-party, 1 corruption replicated sharing. So this multiplicative DPF outputs a replicated share of the values.
Okay, and how does the construction work?
The construction basically works by modifying, this is not in this paper, this is in a previous work that we had. It works by modifying the original 2-party DPF construction in a straightforward way.
So you don't assume you don't make any new assumptions?
No, it's just based on one-way functions.
Okay. Yeah. Sure, thanks.
Yeah, hi. It was a very nice talk, thank you. So for million items, the runtime is about in seconds, a lot of seconds, and communication a lot of megabytes, right? How do you think this would scale to 10 power 9, a billion items?
Right.
Linearly?
So, yes, just multiply the number of items with the bit length of input. So for exact values, you can actually just compute this expression.
Yeah. No, I asked this because if we consider the digital public infrastructure,
right,
in the context of Indian setting, we're already talking about 1.5 billion records, right?
Yes.
Let alone UPI that has hundreds of billions of transactions.
Right.
So I think it would be interesting to really
scale
it to that.
Yes, definitely. The only thing is that you have to be in the specific setting of 2+1 or 3-party setting to get this benefit in the online phase.
What are the challenges that you face in achieving the results as such in an accurate manner?
Sorry, I didn't get the question.
So what are the challenges that you face as such in order to achieve the accurate results as well?
What do you mean by accurate?
So how can you able to draw this conclusion as such by
we just we write down every step and calculated exactly how many comparisons this step makes, and how many invocations of DPF are happening, how many values you are reconstructing in the protocol.
Does it involve any exponential values also?
Yeah, so like in our this DPF based ranking, which is the 4th row, you can see that the computation scales exponentially with the bit length of input. So this is only meaningful for settings where your input bit lengths are small, so 8, 10, 20 max.
Okay. Yeah. Okay.
There's still time for questions. If there are no more questions, let's thank the speaker again.
Thanks.
And I believe that concludes the last talk for today. And there's now a short break, and after that, the photo session.
Yeah, so we are breaking now for 20 minutes, and be here. Don't scatter here and there. We'll get all of you at 4:10, and follow those who have this red lanyard around their neck, and we'll go somewhere to take a photo. And after that, everybody again come back here by 5:30. If you follow us, then there is no problem. But in case you get lost, make to this place by 5.